Great to see you here again. We're going to talk about algorithmic paradigms. Now, what is an algorithmic paradigm? We looked at the different concepts of algorithms in the previous videos, and we've described some specific algorithms. We looked at searching and sorting algorithms. We also looked at the greedy algorithm, where we had an example of the money exchange, and we could see that in certain cases the greedy algorithm would be efficient, and in other cases it would not be. Now, when we look at an algorithmic paradigm, we're talking about general approaches based on particular concepts to construct algorithms. And based on the algorithmic paradigm, it's possible to construct a series of algorithms to resolve a series of problems. Some of those examples include, like I already mentioned before, the brute force algorithm, backtracking algorithms, branch and bound algorithms, divide and conquer algorithms, to select a few. There may be other, or there are other algorithms or classes of algorithms that we can consider. The one we'll be looking at is the brute force algorithm. We already used it before. Let's say when I was looking for the maximum value in a series of numbers, when we were doing matrix calculations and so on. Brute force algorithms do not take into regard the number of calculations or the time needed to resolve it. They just look at all the possibilities. I just try all the numbers, I try all the calculations, and I don't care about the time complexity. Now, this can be very interesting in certain cases. Now, when we look at it, it also means that it can put a lot of strain on the computing time and the computing power of your computers when you are using brute force algorithms. When the numbers are increasing, it becomes longer and longer, and brute force algorithms, when we have a lot of possibilities, may need a lot of computer time, computer space, and that's not always interesting. So we also have other algorithms that can do the same things in less time. There are some examples of brute force. We had the bubble search, we looked at insertion search, and we also looked at finding the sum of all numbers in a series. They are less efficient than other algorithms, and it's certainly the case when we have larger data numbers, and of course when the size of the matrices that we are multiplying is increasing, the time complexity is also increasing rapidly. Now, there are other elements, other algorithms that we can use. We have the backtracking algorithmic paradigm. We also call it depth-first recursive algorithm. And basically we start from a node, an initial node, and we discover the different solutions. For example, we start from a live node 1, we go to the node 1, we have a possibility, we go to the node 1.1, and we find, when we are there, a dead end. So the blue arrows show the way that we are discovering. We reach a dead end, and then we backtrack. We backtrack to the previous node that was live. In that case, it was 1. We look at the node 1.2, and when we continue there, we also see that we end up with a dead end, and we go back and we come back to the start node. Now, the moment that we find out that a node is leading to a dead end, for example, the node 1.1 and the node 1.2 are leading to the dead end, they are not live nodes anymore. Since 1.1 and 1.2 are not live nodes anymore, 1 will also not be a live node. So the next live node that we have is the start node. From there, we go to node 2. So another trajectory we are following, we go to 2.1, we find again a dead end, we come back to the live node 2, and we see that we go to the live node 2.2, 2.1, 2.2.1, which is also a dead end. And finally, we find the solution via node 2.2.2, which is the end node, and it leads to a successful conclusion of the algorithm. There we find our solution. So we basically continue along a leg until we either find a solution or we find a dead end. And when we find a dead end, we return again to the previous live node and try another path. If that path doesn't work, we backtrack again. That's where the name backtracking algorithm comes from. Depth first recursive algorithm. We go in depth first to find a solution, and then we come back. So we always go into the depth. Now, when we are looking at the other algorithms, we also have what we call divide and conquer. And in the divide and conquer step, we have a first step where we have the original list, which is split in smaller subproblems that can be resolved easier. And basically, we continue till we find unique elements in the bottom of that list. The next step is what we call the conquer and merge. So we resolve all the elements at the lowest level, and then we merge them again till we come back to a merged solution, and there we find the solution of the problem. We use this, for example, for a divide and conquer when we were looking at matrix calculations. Another element what we can consider is what we call a branch and bound algorithm. And here we are branching, we are different possibilities that we are considering. So we're branching over those four possibilities. For example, we have four possibilities, A1, A2, A3, and A4. So when we select A1, after A1, we can still select A2, A3, and A4. So basically, we have now already in the node 2, we have one possibility A1, and then we have in the node 6, A1 and A2. In the node 7, we have A1 and A3, and then we have A1 and A4. And now we can continue with the following steps, and we try to find a solution which leads to the end of the branch and bound algorithm to resolve optimization problems. The branches are stopped when the conditions are not met. So once we come to an end, when we don't have the conditions anymore, we don't backtrack, but we continue with some other branches. So the moment we didn't find anything in branch A1, we go to the branch A2, then we go to A3, and then we go to A4. Anyway, we stop when we have a solution. Now, that's what about algorithmic paradigms. The next video will be about the complexity of algorithms. So I will see you in that next video. Thank you very much, and I'm looking forward to seeing you there. Bye-bye.